going to do this reaction. So we are going from, let's see if we have a screenshot. We are going from all AB bonds, low potential energy, to some AA bonds, which has higher potential energy. So the product side has a higher potential energy than the reactant side. So the potential energy wise, reactants have a lower potential energy than the products. And then when it comes to entropy, okay, we have one gas on the product side, no gas on the reactant side. Therefore, we have a higher entropy in the products compared to reactants. Okay, now anyway, so this is what we have. And then it seems like if you draw the Peg diagram, the entropy products have a higher potential energy and a higher number of configurations of higher entropy than the reactants. It seems like option A is the correct answer. So let's select that. Okay, moving on. All right, so you're given this information, you're shown that you're given the two temperatures. Let's do this. You're given the two temperatures. Okay, so T1, T2, and then you're given the activation energy, EA in kilojoules. And then you are asked to find how many times faster the reaction occur at 432.5 Kelvin compared to 306.0 Kelvin. Okay, so for this particular case, we'll be using the Arrhenius equation, which is rate constant is equal to Arrhenius constant times e to the power of minus activation energy over RT. So for temperature 1, it's going to be K1. For temperature 2, it should be K2. So here are my two equations for the two temperatures. The same equation for the two different temperatures. And now, if I want to know how many times faster reaction occurs at temperature 2, which is say Y, and this is X. Okay, then if I divide Y by X, I'm gonna get K2 over K1, and then Arrhenius constant cancels out, and then I have E, and then I have minus EA over R, and within parentheses I have 1 over T2 minus 1 over T1. Okay, now I know activation energy, I know the R, which is the gas constant, I know T1 and T2, I can get the ratio now. Okay, so let's do that. And then if we do that, activation energy is 19 kilojoules. I'm going to multiply by 10 to the power of 3 to make it joules per mole. Divide that by the gas constant, which is 8.314 joules per mole Kelvin. And multiply this by 1 over T2, 432.5 minus 1 over 306. Right, so it should be inverse K. And these K cancel out, moles cancel out, J cancel out, so you're going to get this number here. All right, now let's plug and chug these numbers. Okay, we have 19 times 10 to the power of 3 divided by 8.314, and then that came out to be 2285.3. Okay, so don't forget the minus sign. This minus sign. This is 2285.3. And then for this part, for the temperature part, all right, let's do this. I have 1 divided by 432.5 is 0.02312 okay, minus 1 divided by 306. That came out to be minus 0.000955. 955. All right. Now I have those numbers handy. What I'm going to do is I'm going to multiply these two numbers. Okay, I'm multiplying a negative number by a negative number, so I'm going to end up with a positive number. So multiplying these two numbers, I'm going to get to 285.3. I'm going to get 2.18. Okay, so this is equal to E, the power of 2.184. All right, so now if you get this actual number, and 2.184 is 8.88. 8.88, and they're asking us to give us to one decimal, so I would say 8.9. So let's run with 8.9. To work. Oh, there you go. Perfect. And then moving on, question number 3. The following mechanism has been proposed for the overall reaction. Okay, so and then they're asking for the energy diagram. Okay, which is great. So oral reaction is going to be endothermic. Okay, you're going from all AB on the reactant side to some AA on the product side. Okay, therefore you're going from lower potential energy to higher potential energy. Therefore, it's an endothermic reaction. And yeah, you know what? Let's do this way. Picture. Okay, so it's gonna be endo, because going from low potential energy all AB bonds to high potential energy some AA bonds. Okay. Anyway, so for that reason, I can eliminate this option and this option. So I'm left with the first one and the last one. And then we are also told that the slower step is step 1. Therefore, step 1 should have a higher activation energy barrier. Okay, so here in the first option, here's the activation energy barrier for the first one. And then here's for the second one. Obviously, the first one has high activation energy barrier. So this seems like a valid answer. And then in my fourth option, the activation energy barrier for the first step is this much. And for the second step is much larger, so that is out. Okay, the slower step must have a higher activation energy barrier. Therefore, this option is out. Correct answer is first one. Okay, so let's go with that. Moving on. Consider the following overall reaction for the order of the reaction. So you're given time and concentration data. So what you want to do is plot time and concentration data. Okay, so you can do this in your calculator. I'm gonna do this over here. Let me see. All right, so I'm gonna enter my X values and Y values. So I've already posted how to do such a calculation in the graphing calculator. You do the same thing. You make list 1, which is X values or the time values, and the Y values, which is list 2, the concentrations. And then there you can do list. You can make list 3 and 4, which is for natural log of concentration and 1 over concentration. And then you can evaluate them separately. All right, so let's do this. So for the time values, I have 0, 150, 300, 50, And then for the concentration, values, I have 2.35, 1.2497, 0.6646, 0.3534. All right, and then I can get the natural log of these values. Okay, I'm doing this on Excel now. See, all right, I created my third column or the third list with the natural log of concentration. So you do the same thing, the calculator, and then my list 4 with 1 over concentration. So you go up to list 4, and then when you have the equal sign, you type 1 divided by, and then second, and then stat to select the list. And then you're going to list the values in list 1. So that's what you do in your calculator. I'm going to do this here with Excel for now. Then I have those values now. Second. All right. What I'm going to do is I'm going to plot these graphs separately. First, I'm going to plot concentration versus time. And then make sure that you get the linear regression value as well. Your calculator, you can do that. I'm going to do this on my Excel for the moment. All right, so obviously the zeroth order graph, concentration versus time, is not linear. Okay, it's like linear regression value is 0.93, and then okay, it is very obvious that it's not linear. And now I'm gonna do the same thing for natural log of concentration versus time, which is pretty linear. R squared is 1, which is great. And then 1 over concentration is not linear. The R squared is 0.93. So based on the graph, natural log of concentration versus time graph is linear, and therefore the order with respect to concentration A is first order. So I'm going to select that, right? And then if somebody asks for the rate constant, you can do that as well from the slope. The minus negative slope is your rate constant. All right, anyway, so this is what we have for now, first order. Moving on to question 5. The following data corresponds to reaction with the following rate law. So rate law is given. Okay, so it is first order with respect to B. Determine the rate constant for this process. So I need to replot the values again. All right, give me a second. I'm gonna do this. All right, so my time values are 0, 0.1, 0.3, and 0.5. The concentrations are 1 times 10 to the power of minus 4, power of minus 4, and then I have 8.19 times 10 to the power of minus 5. Okay, and then I have 5.49 times 10 to the power of minus 5, and then I have Yeah, so I'll show you a trick in a minute as well. Okay, if you know something about this, we have a shortcut here. I'm going to show that in a second. 3.68 times 10 to the power of minus 5 minus 5. All right, so I just plotted them. Okay, and then right away I got if you plot concentration versus time, natural log of concentration versus time, and 1 over concentration versus time, you're going to see that natural log of concentration versus time is going to be linear. All right, and how do we know that? So it's from the units of the rate law, of the rate constant. Okay, you see that all of these have per time units. Okay, so for first order reactions, you know, the rate law is rate constant times the concentration of the species. Okay, so rate is always concentration over time, and then units for the concentration is concentration units. Okay, now for the units for K should have per time units. Okay, it's a per time, or 1 over T. So in this case, we see that we have 1 over hour or per hours. That means it should be a first order reaction. Okay, anyway, so that is something we can admire right away. And also to get the rate constant now, we can do this in 2 different ways. We actually, so right now we have the data here. I plotted the graph already, and I see from the plot the slope is equal to minus 1.9995. Okay, so and this is per hour, right? And then this is equal to minus rate constant. Of the rate constant is plus 1.9995, in other words 2 per hour. Okay, so the correct answer is this guy over here. Okay, yeah, and then the other thing we can do is we can pick 2 points, right? So let's see. I'm gonna try this out anyway. So let's pick this one and this one. Okay, natural log of concentration at 0.1 is equal to minus rate constant times time, which is 0.1 hours. Okay, plus natural log of the initial concentration, which is at 0. So we know that, so from this we can say that KT is equal to natural log of concentration at time 0 minus natural log of concentration at time 0.1. Okay, and then therefore K must be equal to these values, difference of natural log of 0 minus natural log of 0.1 divided by time, which is 0.1 hours. Okay, so let's try this. So ln initial concentration is natural log of 10 to the power of minus 4 minus natural log of time concentration at time 0.1 is 8.19 times 10 to the power of minus 5. Divide this by 0.1 hour should give you the rate constant. All right, so let's see what we can do. We should be able to do this in our calculators as well. I'm gonna use this as is. I'm not gonna do my division from the subtraction thing here, but let me use the same values. ln of 10 to the power of -4, okay, minus ln of 8.19 times 10 to the power of -5. Okay, so I got in the numerator 0.1997 divided by 0.1 hour. Okay, so this is equal to, so if you divide something by 0.1, it's like multiplying by 10, right? So you're going to get 1.997 and it should be per hour, which is the same answer we got here. So anyway, so that's something we can do if we know, when we're familiar with these questions. Okay, so based on, again, what I did was this. Okay, if you don't want to plot, if you don't feel like plotting a graph and then doing all that stuff in a calculator, you can pay attention to the units. Over here you can see that we have per time units that is consistent with the first order reactions, first order rate laws. Okay, and then integrated rate law for the first order reaction is this guy over here. Okay, and then we know the initial concentration, which is this guy. We know the concentration at time, say any time t, 0.1 over here, and then we know the time because that is 0.1, and the only thing we do not know is k. We can find that. That's it. That's the other way of doing it if you don't want to plot anything. All right, that's enough of that. Move on. Let's put that. All right, consider the following reaction mechanism and its associated in each diagram. Nice. So you see that you only have to determine few things here actually. All right, so you need to have delta G versus temperature. Let me show you what I would do. Now, to do this, to know delta G versus temperature, I need to know delta H. Okay, I know delta H is less than 0. How do I know it? We are going from high potential energy reactants to low potential energy products in the overall reaction. Okay, therefore delta H is negative. And also, if you look at this, if you look at the overall reaction, you have gas molecules on the reactant side. Okay, so if you don't see it here, I'll do it. I'll show the overall reaction here. C2H4 cancels out because it's an intermediate. So is Br minus. Okay, and you're going to end up with C2H4 gas and HBr gas on the reactant side, and on the product side you have C2H5Br liquid. So you're going from to gas to no gas. Okay, that means you are decreasing the entropy. That means delta S is negative as well. Delta S is negative as well. Okay, so if we have both delta H and delta S negative, that means this is product favored only at low temperatures. Okay, that means delta G is negative. Here's 0, here's my delta G, here's my temperature. Delta G is negative or product favored only at low temperatures. Therefore, you should see a graph like that. That's it. That's all you have to do there. All right, so let's select that, which is the fourth graph. Moving on, question 7, consider the following reaction mechanism and its associated diagram, blah, blah, blah. And based on the rate law for the overall process, predict how many times faster the reaction will be if the concentration of C2H4 is increased by a factor of 2, blah, blah. All right, let's do this here. Now, based on the energy diagram, right, the first step is the slower step. Therefore, the rate law is rate constant times C2H4 times HBr. There's no doubt about that. Okay, there's no other simplification as well. Okay, slower step determines the rate of the entire reaction. That's the rate determining step. All right, and then okay, then what we're told is this is rate 1. Okay, and then in rate 2 we have the same rate constant because we are not changing the temperature. What we're doing is we are increasing the C2H4 concentration by a factor of 2. So instead of C2H4, we have 2 times C2H4, and then HBr, and the concentration of HBr is increased by a factor of 8.5. And then here, instead of HBr, we have 8.5 times the HBr concentration that we had initially in rate 2. Okay, and this is my 1, this is my 2. What I'm going to do is I'm going to divide 2 by 1. To do that, I'm going to get rate 2 over rate 1. All right, and then let me cancel things out. That's my favorite part. K cancels out, C2H4 cancels out, HBr cancels out, and in the numerator, I'm going to get 2 times 8.5, which is 17. So rate 2 is 17 times greater than rate 1. Yeah, how many times faster the reaction will be? It should be 17 times. So that should be the answer. So let's try 17. Nice. Okay. It's question 8. Again, the same thing. Energy diagram wise, and then determine the time required for the concentration to be 0.05 into your calculator. Okay, so anyway, let's do this here on the screenshot. Okay, now again, the first step is slower step. We know based on that the order with respect to C2H4 is first order. It's the same rate law as before, right? So rate is equal to rate constant times C2H4 concentration times HBr concentration. Now what is important for us is this first order with respect to C2H4, because we are given C2H4 here. Okay, that's all that matters. Anyway, and then the thing is, you are given a concentration. Okay, you are asked to reach this concentration, how much time will it take? Now, whenever we are given problems like this, where concentration and time are related, we need integrated rate laws. Okay, for first order reactions, integrated rate law looks something like this: natural log of say initial concentration. Yes, fine. Initial constant. No, I'm sorry. Let me see. Okay, for the first order reactions, natural log of concentration at time t is equal to minus rate constant times time plus natural log of the initial concentration. Okay, and then what we need to do is, so we need to know what we know from this. All right, so we know the concentration at time t should be 0.005. We know the initial concentration, which is blah 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 6.3 times 10 to the power of -2, which is great. And then t is what it's asking. Do we know the rate constant? Yeah, we do not know the rate constant here. Okay, so we need to find that. So that's something we need to do. We need the rate constant. Okay, so how to find the rate constant? There are 2 ways, but at this moment, based on what we have learned, we need to plot the graph to get the rate constant. So let's do that. All right. So what we have is, let's see, we have 0, we have 5, 8, and 12. All right, that is more than I need. So 4 data points is enough. I'm not going to plot everything. And then I have, for the 0 concentration, we have at time 0, I have a concentration of 6.3 times 10 to the power of -2. And then at time 5, I have 4.6 times 10 to the power of -2. And then at time 8, we have 3.8 times 10 to the power of -2. Then at time 12, we have 3.3 times 10 to the power of -2. Okay, so 3 times 10 to the power of -2. So what we have, and then we are going to plot the concentration, natural log of concentration versus time. Okay, and then when we do that, we see that our slope from that, I need a different color. I don't like that because it's not that obvious. Right, we see that the slope is minus 0.062. Okay, and then therefore this is going to be minus rate constant. Therefore, the rate constant is 0.062 per time units. Okay, so all right, so they're not given the units here, but time can be hours, seconds, minutes, so whatever. All right, so we know the rate constant now. All right, so we know this as well. We just found that. Okay, now what we're going to do is we're going to plug. We can either plug and chug, or we can. What I'm going to do is I'm going to have an expression for t. So I can write this as kt is equal to natural log of initial concentration minus natural log of concentration at time t, and therefore t is equal to natural log should be anyway r naught divided by rt, or you can say natural log of rt divided by constant. Okay, so we'll plug and chug. Yeah, natural log of 6.3 times 10 to the power of -2 here, minus natural log of RT is this. They need 0.05, 0.0. Let's see, I'm going to do this in a different way. So we have 5 times 10 to the power of 1, 1, 2, 3. 10 to the power of -3 over here, and divide this by the rate constant, which is 0.062. Okay, so let's do this calculator. So we have we have 6.3 times 10 to the power of -2 minus 5 times 10 to the power of -3. Okay, and then we need to divide that by the rate constant, which is 0.062. Okay, it says 85.47. This gives us 85.47. Conventional number with one decimal should be 85.5. Let's try that. Okay. 85.5. Okay, so let's see. The following mechanism has been proposed for the overall reaction, blah, blah, blah. Determine the overall rate load should be determined by the slower step, which has NO and 2. So there's nothing else, not the first one. It should be the third option over here. Straightforward. And then question 10, which of the following statements are true about the effect of increasing temperature on the following reaction? So we are increasing temperature, it will reach the equilibrium faster. That is true. Okay, the reactions are going to go faster when you increase the temperature. That is correct. Okay, and number 2, it will produce a greater amount of SO3. Now here's the thing: SO3 has a lower potential energy because it has AB bonds. Okay, AB bonds means stronger bonds means lower potential energy. Therefore, increasing temperature will not produce more of SO3. It will facilitate the formation of the state with weaker interactions, which is going to be reactants. So which is going to be incorrect. 2 is incorrect. It will decrease the equilibrium constant value. So if it is not producing SO3, that means if it is going to start favoring the reactants, that means yes, it's going to decrease the equilibrium constant value. So 1 and 3 are okay. And then last one, it will decrease the rate constant. No, it can't decrease the rate constant. It's going to increase it. So 1 and 3 are the only correct answers. Question 11, because the following mechanism. Okay, so let's see. So they're asking what is the role of H plus in this process. So H plus is a reactant in the first step, and also it is ending up as a product in the second step as well. So it is not consumed during the reaction. It participated in the reaction, but it's not consumed. So things like this are considered as a catalyst. So 2H or H plus should be a catalyst in this reaction. All right, so the last question, use the following data for the rate constant of a process. For the rate constant, data for the rate constant of a process at different temperatures to estimate the value of activation energy. So again, this is using, let's see if I can do this, right? So we can use the Arrhenius equation, which is rate constant is equal to 8 times e to the power of minus EA over RT. If you take natural log on both sides, we can say natural log of rate constant is equal to minus EA over RT plus natural log of the Arrhenius constant. So if you plot 1 over T on the x-axis, it's a different color, 1 over T on the x-axis and natural log of K on the y-axis, the slope of the graph will give you the activation energy divided by R. Okay, and then the y-intercept is the natural log of Arrhenius constant. Okay, that's it. Now what we can do is we're going to plot this and see what we're going to get. All right, so my temperature data are 300, 310, 320, and 330. Oh, 30. Great. And then for my rate constant values, we have 0.134 and 0.2027 and 0.2988 and then 0.4301. All right, and then I'm gonna, in my list 3, I'm gonna make 1 over temperature. Okay, go to list 3 and say equals 1 divided by second stat and select list 3 on your calculators. Okay, so I'm going to do that for my Excel now should be 1 divided by 300. That. Okay, I have the 1 over temperature values. And then I'm going to have natural log of K values on my list 4. Again, go to list 4 equals natural log second stat, select list 2 or number 2 from that list, and then will give you natural log of your list 2 values. In this case, rate constant values. All right, once you have those values, you can evaluate them. All right, I'm going to plot because I have Excel. If I plot ln concentrate, ln rate constant versus 1 over temperature, I'm going to get a linear graph, and then trend line shows me the slope is equal to minus 3848.5. 3848.5. 3848.5. Okay, and then we know that this should be equal to minus activation energy over R. Okay, so that means plus, therefore the activation energy is equal to 3848.5 multiplied by R, which is 8.314 joules per mole per Kelvin. Per mole per Kelvin, and then here this is in Kelvin, so Kelvin cancels out. Anyway, and then this number is, let's see, we have 3848.5 multiplied by 8.314 to be okay, anyway, still is 31,996. 31,996.43. Okay, and then yeah, so the answer they're asking is in kilojoules. So this is in kilojoules is 31.996, which is around 32 kilojoules. So that should be your answer. Right, 32 kilojoules. Okay. So let's submit that. Submit the quiz. I did 32 here. Anyway. So I mean, we selected 32. I mean, yeah, it didn't allow me to submit 32 because I exceeded the time because I started recording this a little bit late. Okay. Anyway, so again, the correct answer is 32 kilojoules, which we got. All right. So yeah, I hope this helped. I'll see you guys in class. Bye, everybody.